Anybody have any questions before we get started? We can still got plenty of time. I just want to check. In my butt. Yeah, baby. Well, finally got that done. All right, I still got about 3 minutes, so feel free to ask me any questions if you have any. I got home today, took a nap, so my hair's all messy. All out looking all bushy. I don't know if I like this anymore. Not like that, that's for sure. Gotta be super cool for that you have a comb for your beard. Super nerdy want to. I'm not sure. I should try to do share screen, make sure that's working. Should give that a try. So it is working. Let me stop share. Oh, it's ready to roll. Okay, we got 1 minute left and we only got 5 people in here. It's a little fewer than we're supposed to. I love my books back there. Let's see. Mageddon. The Quran, the Bible, let's see. All those books. You got a trig book. Oh, that's Jefferson's Bible. And I got Jefferson's Quran. I got Word Smart. Let's see if I get okay. Got Bishop's Boys about the Wright brothers. I think I got a book down there on global warming. Anyways, all right. So it's time to start, everybody. Anybody have any questions on any past homeworks or anything? Hopefully you remember that we do have some tests that are due. Here comes another person. Just as a refresher, let me pull open that module so I can see and remind you just in case. So currently we have test 1 is due on the 13th, which is tomorrow night at 11:59 p.m. And then test 2 is due on the 18th. And that covers chapters 19 and 20. We'll be finishing off 19 tonight, maybe even getting into 20, but 20 is really short either way. So even if we don't get into it, it's still going to be done the next day. So yeah. So the online test, remember that's an online test, open notes, open book, open any book. You can even do Google searches. The only thing is you're not supposed to look at anything created after this was posted. And that's just a way for me to make sure or to request that you not have anybody that's already seen the test help you. It looks like there's been quite a few people already taking both tests and you get multiple attempts and only your highest count. So get that done so you don't miss any. But like I said, it does have it grayed out, so I know at least one person has taken each of them. But anyways, no questions on any of that? All right.
I have a question.
Yes,
Mr. Younger.
I have a question.
Remember, I had a 0 on my first and second attempt on my
oh yeah,
online
I can
test.
clear that. I think I can clear
Yeah,
it. Is that test 1?
yeah, online test 1.
Okay, so what I'm gonna have to do is I remember now, I can't clear it, but what I'll do is give you 2 extra attempts. So let me see.
Okay.
And this is saying, right?
Yes.
Okay. Yeah, so I'm gonna give you 2 extra attempts. So
Thank you.
you should get 3 that aren't 0, hopefully.
All right, thank you.
Dang, you did such a bad job. You got a 0, man. No. Yeah, it's
Yeah, I couldn't see the
question,
problem
right?
for first two attempts.
Yeah, it didn't have any questions in there, did it? So yeah, I'm not
Thank you.
giving him any break. Poor guy just got there early. Actually, it wasn't even early. It was just something happened and my test didn't copy. All right. And there was another person, was it John maybe that asked the question too?
Yeah. I had a question about one of the emails you sent. So is test two face to face
Originally it was planned to
or
be, but now that I've seen that, basically what happened is I was looking at an old version of my lab schedule, and I thought the test that we're going to take in lab was like a whole week, maybe even 2 weeks earlier than it was. So I was only going to be able to fit in one online test before the face-to-face test. But now I've got plenty of time. The test is supposed to be like on the week of the 25th. Actually, let me double check what that is. Actually, I can. I don't have it with me. Oh, yeah, I do. So the test, you guys meet, what day of the week is your lab?
Tuesdays?
Tuesdays. So your test will be on the 24th. So since we had till the 24th, I'm definitely getting 2 online tests before then. I might even get a third. And then your test will be the test that you have face to face will be maybe the last chapter that online test tested plus one more chapter or something like that. But you'll know more than a week, or at least a week in advance, of what that face-to-face test is. So like I said, I'll know next week, and right now it's the 12th, so I'll let you know next week. And the 24th is basically, well, 2 weeks from today. So any questions on that? All right, got more people coming in. Your towels.
The 24th.
Yeah, well, that's what it's saying here. Let me see if you've got a date error. Looks like the 24th falls on a Monday, doesn't it? Nope, falls on a Sunday. No, that's September. So 24th does fall on a Tuesday. So yeah, it'll be 24th. Today is, oh, that's October 24th. I'm looking at the wrong one. So no, it'll be the 19th, which is a week from today. So today's the day I'm supposed to decide. All right. So yeah, that's no problem. What we're going to do is we will only have, sorry, I thought I was a whole other week out. I'm thinking of my class that meets on Monday. They got another week beyond that. So yeah, when test 2 is done, I will put up a practice 3 test. I'll probably put that up today just so I can start practicing. That test will be on chapters 21 and 22. But like I said, all tests are cumulative. So there's a chance you could have questions from 17, 18, 19, 20, 21, and 22. So 21 and 22 is what we're shooting for the test on the 19th. That'd be a week from today. I'm 100% sure we're not getting to 22. So we probably just say it's going to be 20 and 21. So that obviously being 20 and 21 and 20 being so short, that means it's probably going to have a lot more from 17 and 18 and 19. So the face-to-face test, which will be in lab 1 week from today, will cover chapters as far as chapter 20 and 21, and that's it. Okay. But like I said, it can cover anything before that.
Is that one multiple choice? Like is it basically the same like format as all the online
Usually,
tests?
but the face-to-face test, sometimes I have one where you have to turn in your work. Sometimes I have one where it's open response. So it's not a multiple choice. It's just, you got to turn in an answer. Sometimes I have one where it's multiple choice, but you got to turn in the work to show a derivation. But usually it's only like 1 or 2 problems out of all of them that have to do that. And the rest is just a regular multiple choice test.
Okay, so it's like the midterm and final, like last year.
Exactly. Yeah.
Okay.
Okay. And since we got 3 of them, there's less pressure on me to make it fancier. So it might be closer to like the online test than normal. Okay. Anybody else? Looks like I got everything going here. I saw, yeah, someone else was coming in. I knew that was coming. Okay. So now we're up to 12 people in here. That's good. So let's get started. When we last talked, had covered, actually, let me double check what I had covered. That was 242 way back on, nope, that's 241. That's 241. Everything in here is 241. That's 242, totally unrelated. 242. There it is, the 7th. Oh yeah, we had just got up to the various processes. I'd talk about specific heat, that sort of stuff. So what I'm going to do now is I'm going to try to bring you up to the rest of chapter 19. So let me get you started on that. As far as chapter 19 goes, we're starting to get into the molar specific heat. Something really interesting happened, so I'm going to share my screen with you right here. If you decide to work on specific heat, and remember, specific heat is the amount of heat required to raise 1 gram of substance 1 Celsius degree. And so that's if you do calories per gram per Celsius degree. But there's also, I did the wrong one, but there's also another way you can do it. And what we're showing in this graph right here, or in this table right here, is that evidently if you use gram or calories per mole or joules per mole, you get a fairly weird response. So let's look right up here. So this is CV and CP in these 2 columns, and that's in the typical kilocalories per gram per Kelvin degree. We were using calories per gram per Celsius degree, but a change in Kelvin is the same as a change in Celsius degree, so that's okay. And a kilo divided by a kilo is the same thing as a cal divided by a gram, so that's okay as well. But you see that these values have very different values. Not only are there 2 different ones, this one C sub V is the specific heat if you maintain a constant volume, and then C sub P is the specific heat if you maintain a constant pressure. Now, I want you to think about this. You're thinking about applying heat to a substance, say helium, and it's a gas. And if you hold it at constant pressure, then basically you can have work being done, because work is equal to the integral of P dV, but P being a constant means work is equal to P times the change in volume. Now, if you do if you add heat to the same gas, but this time you actually hold the volume constant, then no work can be done. So every bit of heat goes into changing the temperature, as opposed to, say, lifting a piston head or something like that. So you can see from that argument why C sub V and C sub P have different values. And you should, in fact, see why C sub P should be larger, because C sub P, some of the heat goes to raising the temperature, which is the key aspect of specific heat, but some of the heat can go to work, which is, sort of unrelated. That's not really what you care about when you're trying to raise the temperature of a gas. So that's one thing. You see 2 different values, CP and CV, but look how much they differ. So helium and neon, which are both monatomic gases, and usually we can treat them as ideal gases, but notice CV is 0.75 for helium, 0.148 for neon. If you go to diatomic, it's 0.177 for N2 and 0.155 for O2. And if you go to triatomic, like CO2 and water, it's 0.153 and 0.350. It's almost no rhyme or reason on what these values are. But if you make one little change, if you change from calories per gram per Kelvin to calories per mole per Kelvin, look at this. This is essentially 3. So CV is essentially 3 for helium and neon, and CP is essentially 5 for helium and neon. If you move down to the diatomic, then CV is essentially 5 for both nitrogen and oxygen, and it's essentially 7 for CP for nitrogen and oxygen. And you can see how much more regular they are. Not only that, this amazing fact falls out. If you do CP minus CV, you consistently get 1.99, 1.99, 1.99, 2.00, 2.03, 2.00, 2.05. So really it's like, 2.5% difference from the worst to the best of CP minus CV being 2. So, and if you remember correctly, R, the ideal gas constant in calories per mole Kelvin, is 1.99. So that's essentially 2 as well. So what you see from this table is this is actual experimental data, and it appears that CP minus CV is consistently right about R. And in fact, we can do a derivation. Your book does the derivation. I'm not going to do it. I've done it in the past, so you can find it on my YouTube channel if you'd like, or you can just read it in the book. But you can do a derivation and show that CP minus CV for an ideal gas under certain conditions is really just R. And then you can do a further derivation, and what you'll find is CP, which is the larger of the two, is 5 halves R, and CV, the smaller of the two, is 3 halves R. So that's the major discovery that we make when we start looking at ideal gases and we start dealing with specific heats that are molar as opposed to mass. So with that in mind, let me write down the results. I just said them, but I'm going to stop sharing the screen here and I'm going to start sharing my iPad screen. So here that is, there's that. So it should pop up any minute now. Looks like it's still trying, so that's cool. We'll move you over here. Pull out the chat so I can see that. All right, so we got this. Yes, you are allowed to have a formula sheet on the face-to-face test. I highly recommend you start making that now. And you do that by going to chapter 17 and just write down every chapter from the very first page of chapter 17, every equation that has a parenthesis. And then chapter 17 will say 17 dash, and then it'll say a number and then close parentheses. Every equation that has that, you're allowed to have on your equation sheet. So I'd go ahead and start doing that, get that for chapter 17, then do the same thing for 18, then for 19, and just keep them the whole semester, okay? Because I don't have a limit on the number of pages you can have, that sort of thing. All right, so now that we got that, what we discovered was CP, and they use a capital for this. CP is going to turn out to be 5 halves R. CV is going to turn out to be 3 halves R. And that all came from, so I'll put the arrow pointing this way, that all came from the fact that CP minus CV is equal to R. Okay. R is equal to ideal gas constant, which is 1.99 calories per mole Kelvin, like that. Okay. So with that in mind, that's kind of neat. Then we go on and start talking about the internal energy for an ideal gas. So ideal monatomic gas. We can do the derivation of that, and in fact, your book does it. Again, if you want to see it, look that up in my YouTube channel, and you can see me doing it, or you can just read the one in the book. It's really good. It's really the whole trick with physics and statics and dynamics courses. A lot of learning comes from you trying to fill in the blanks from what the author tells you and shows you equation form to what they actually put in the book, because they'll skip steps and stuff like that. And you don't really fully understand the derivation until you can do it yourself and you understand each step and can fill in all those gaps. So I highly recommend doing that. But what we get for the ideal monatomic gas is the internal energy, which a lot of books call U, your author's calling it E internal, is just going to be 3 halves. nRT is one case, but it's also 3 halves of capital N KT. Do y'all remember the difference between capital N and lowercase n? So the lowercase n is the number of moles. So it actually has some relevance to the total number of atoms or molecules. The uppercase N is the total number of molecules or atoms. These are all monatomic. So it's basically N, and big N is about the number of atoms, but little n is the number of moles, whereas big N is the number of atoms. When we get into a diatomic gas, then you have basically molecules. They can be molecules, though, that are made of 2 identical atoms like H2 and O2 and N2. In that case, then it's again molecules, even though they're made of the same stuff. It's called molecular hydrogen or molecular oxygen or molecular nitrogen, that sort of thing. So we can interpret this, and in fact, we did this derivation more or less when we were doing the derivation of the kinetic energy of the molecules in an ideal gas. We basically came up with this 3 halves stuff. And if you remember correctly, basically 1/2 kT was allotted for the center of mass moving in the X direction, so left, right. 1/2 was for moving in the Y direction, so you might call that in and out. And then another 1/2 was for moving up and down, so you might call that the Z direction. So that's tipping its hand to show you something called the equipartition theorem, which I've mentioned to you before. But basically what we say with the equipartition theorem is when you have a really huge sample, and I'm talking like Avogadro's number is huge. So that's 10 to the 22. So when you have that big a set of numbers, statistics works really, 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 really well. And statistics would say that if you have 10 to the 23 molecules or 10 to the 23 atoms, and you've got exactly 3 ways to divvy up the energy amongst them, then the 3 ways will have exactly 1/3 of the total energy. So that's what I mean by 1/2 kT, 1/2 kT, 1/2 kT. Each of them is a third, and it's going to be exactly that. That's what the equipartition theorem says. Now, if you happen to find, 10 to the 23 or 10 to the 22 molecules or atoms or something, and it has, say, 5 different ways of energy, then in that case, each one's going to have exactly the same amount of energy, each of the 5. It turns out that because of the same derivation, each one will have 1/2 kT. So that'd be 1/2 kT, 2/2 kT, 3/2 kT, 4/2 kT, 5/2 kT. And if you look experimentally, there turns out to be something really neat when we go up to the next molecule. So the equipartition theorem says that each tranche, if you will, or each type or style of energy has exactly the same amount of energy in it as every other type. And that in this case, it turns out that each way has 1/2 kT of energy in it per atom. So that's why it's 1/2 kT, and then there's a capital N by it because you didn't have to multiply it by the total number of atoms or molecules or whatever. So that's where we're going. Let me stop sharing for a second, and let me go back to sharing the screen from the book to show you something else. So what you need to see is, I'm looking for it over here. Specific heat, equipartition of energy. Here it is. So this is really what happens. Notice this is molar specific heat, C sub V, as a function of temperature for hydrogen molecules. So this is molecular hydrogen, H2. And what you see here is, yes, H2 is diatomic. And what I told you earlier is that for an ideal diatomic gas, and I'm writing this on here, you'll see it in a second, but an ideal diatomic gas, you end up getting E internal. And I'm going to put a question mark with an equal sign with a little dot over it, just to remind us that the experimental evidence I'm going to tell you here makes this not necessarily true. So that's why I put the little dot in here, and you'll see it in a second. But it's 5/2 N kT. And again, I'll show you that in a second. But what we're looking at right now is a graph, and it turns out that, yeah, hydrogen does have more degrees of freedom than 3, because for the hydrogen diatomic molecule, you've got hydrogen, the whole molecule, which is like a dumbbell, basically. That whole molecule can move as its center of mass moves. It can move to the left and to the right. That's 1 degree of freedom. That's 1/2 kT for 1/2 mv squared. It can also move in and out. So that's another 1/2 kT. In that case, it's 1/2 kT for the 1/2 mv squared in the Y direction. And then it can also move up and down. That's another 1/2 kT, which is for a 1/2 mv squared in the Z direction. So that's the 3/2 kT you'd get for both the diatomic and the monatomic ideal gas. But because it's a dumbbell, it actually also has the ability to rotate this way about an axis going this, right? But it also has the ability to rotate this way about an axis going straight down. So that's 2 more degrees of freedom that are associated with rotation. Now, it also could rotate about an axis going this way, but that's literally just the individual atoms rotating. So that's not a significant amount of energy. So you really only get those 2. Now, that's what happens, and you get 5/2 kT because each of them, according to the equipartition theorem, get an equal amount. And then according to our discoveries, each of them get the amount 1/2 kT. So you're going to get 3/2 kT for it going left, right, up, down, and in, out. And then you're going to get 1/2 kT for it rotating about an axis coming out of the board, and then another axis going straight up. You get another 1/2 kT. So you think that's sort of the formula, and that's what I wrote down. But if you look at this graph down here, what it shows is that around temperatures from, say, 20 Kelvin up to about 60 or 70 Kelvin, you're only going to get 3/2 kT or 3/2 R for the actual specific heat. Okay, so this, again, this relates to the internal energy as well, but I'm talking about this the CP and the CV. In this case, we're talking about the CV. So you're only going to get 3/2 when you're down around 60 Kelvin. If you boost it up to around 120, 150 Kelvin, then all of a sudden you're getting the 5/2 R for the CV, or the 5/2 kT in some sense for the internal energy, which is what we sort of expected. But here's another weird one. It turns out if you get over 1,000 Kelvin, start getting around 2,000 Kelvin, lo and behold, it comes up to another 7/2 instead of 5/2. And in that case, the way I tell my students is basically there's some forms of energy that you run into, and they all have like some constant times 1/2 times something squared. So you know one of them, that was the first one we did for the 3/2. That's 1/2 mv squared. So you had a 1/2 mv squared for left, right, a 1/2 mv squared for in, out, and a 1/2 mv squared for up, down. That's your 3/2. Then I said, well, there's a 1/2 I omega squared for rotation. That was about the vertical axis. And then there's a rotation about the axis pointing into the screen. That's another 1/2 I omega squared with a different I, of course. So that's 5. But it turns out that you also have 1/2 kx squared for the diatomic molecule vibrating like it's on a spring. So 1/2 kx squared. But you also have the kinetic energy associated with that 1/2 mv squared, but due to the individual molecule going this way for this case and this way for this case. So that's where you get the other two. So that's a key thing to understand. I just wanted to make sure you guys knew that. Now I can go back to the molar specific heat, which you'll see here. This is where they're doing the derivations and various things. You can see this is, for instance, the first law of thermodynamics, and they're working it out. So that's where they get CP minus CV's R. If you take a constant volume situation, then no work can be done. So the first law of thermodynamics gives you delta E internal is just Q sub V, and the V is down there because it's saying, hey, this is constant volume. Now, if you take E internal for a diatomic gas, then you're going to basically get 3/2 nRT. And with that, you can get CV's 3/2 R. So that's where all that derivation stuff comes from. Not that big of a deal, but the main thing is I wanted to show you that. Here's the equipartition theorem that I was just showing you. If you move on further, they talk about solids. Again, the law of dual length with heat and stuff like that. Those are things that are good conceptual questions. So you definitely should read over this and try to make sense of it. This is a nice little section where it's literally one paragraph, so it's not that hard to read. But if you continue on, it'll go through more derivations. So here's an adiabatic expansion. And with that adiabatic expansion, you ultimately get this cool principle right here that P, the pressure, times V raised to the gamma power, and gamma, by the way, is C, capital C sub P divided by capital C sub V. So this the 5/2 divided by the 3/2 basically gives you 5/3. That's what gamma is. So P times V to the gamma is a constant. So that's a whole nother equation that we get access to, provided it's adiabatic. And in fact, I think this is the example I'm going to want to do. So I'm going to stop sharing for a second, go back to sharing my iPad so you can see what we've concluded. I'm going to do this, pull up this, pull up that. All right, so we got the ideal monatomic gas and the ideal diatomic gas. This is where I put the dot over the equal symbol. It's going to come up in a second. It's not, yeah, there it is. Okay, see how I have the dot over the equals? That's just reminding you that that experiment suggested it was 3 halves. This is CV, by the way, was 3 halves. Then it went to 5 halves. Then it went to 7 halves of R. And that's not to the R, that's times R, by the way. So that's why I put that little dot on there to keep track of that. That's the ideal diatomic gas. It gets even more complicated with a polyatomic gas. So you can start off with triatomic like H2O and CO2 and stuff like that. But you can go to more complex things like dang it, I'm drawing a blank on C2H6, but anyways, it's not benzene. I can't remember. Anyways, anyways, with more complex molecules, you get even more degrees of freedom and stuff like that. What we did find, of course, was CP minus CV is equal to R. We found that CP was 5 halves R, CV was 3 halves R, and all that good stuff. Now, we already had the ideal gas law, which said PV is equal to N times R times T. And we could also use that in a more general way. In other words, even in cases where it's not behaving perfectly like an ideal gas, it turns out that P1 V1 over T1 is equal to P2 V2 over T2, or any combination thereof. So you could say P1 V1 is equal to P2 V2, or you could say P1 over T1 is equal to P2 over, oops. I don't like anything I wrote about that. Okay. P2 over T2, that's another one. Or you could write, for instance, V1 over T1 is equal to V2 over T2. Those are all different ways you could write the same thing. And that's for all ideal gases. So all this stuff right here is just for ideal gases. Nothing else. I mean, you don't have to have any other conditions. But if you consider an adiabatic process, and remember, that is Q equals 0. If you choose an adiabatic or examining an adiabatic process, then you get this other version that is P1 V1 raised to the gamma power is equal to P2 V2 raised to the gamma power, where gamma is defined to be CP over CV, which experimentally and theoretically is about 5/3. Okay, so that's a whole new different thing we can do. This is the new stuff that we have access to. All I'm asking you is that you be able to do the examples in the book that are like it. And I'm going to start off by showing you one of those right now. So if we look right here, it says an ideal monatomic gas is compressed starting at point A in the PV diagram. I'll draw this diagram for you in a second. So this is going to be example 19.5. And basically what we have is I will draw a coordinate system. And this is going to be your V. And this is going to be your P. And in fact, this is going to be, well, actually, I should probably go ahead and just so I can remember the points and everything. This one's going to be in cubic meters, and this one's going to be in kilopascals. Okay, and this one's 1.00. That's 1, 2, 3, 4, 5, 6, 7. Oh, that's helpful. So that's 7. I'll go to 3.5, and that'll be 0.5 right there. Okay. Now I'm also going to come up here to 100, which I'll say is 2. So here's 100 kilopascals.
We cannot see the iPad.
Oh yeah, thank you. Duh. I changed it and then forgot that I had changed it. All right, so yeah, since I'm looking at and actually I didn't even show you this computer screen, so I was doubly stupid. So here we go. I hate how long it takes to switch from screen to screen. It's aggravating. Okay, so this should come up any minute now for you. Maybe. Ah, there it is. All I had to do is act like it wasn't. Okay. So what's going to happen with this process is we're going to initially start at 100 kilopascals and 1 cubic meter. That point is going to be called point A. And then it is going to run from 100 kilopascals, excuse me, from 100 kilopascals and 1 cubic meter to somewhere in between, which I'm going to say is B right here. So that's B. And then it's going to go from B to C, which I'm going to say is right here. Okay. Now this process from here to here is an adiabatic process. And this process, whoa, Nelly, this process from here to here is isothermal. And remember, isothermal means delta T is equal to 0. Okay. Now you should be able to see this, but this is exactly why I drew it on here, is so you'd see exactly what it is. You'd see that this corresponds to 100 kilopascals. This corresponds to 200 pascals. And in fact, this one we don't know, and that one we don't know. Okay. So the problem we're actually solving is one for that particular graph. And as I told you, it says an ideal monatomic gas is compressed starting at point A in the PV diagram, where PA is equal to 100 kilopascals. So I've got that drawn as point A. VA is equal to 1 cubic meter. I've got that drawn. Now TA, this is additional. I didn't draw this on the diagram, but I can say that TA is equal to 300 Kelvin. So that's kind of helpful. The gas is first compressed adiabatically to state B. So that's what we're showing with that little arrow on a curved line. And then it says adiabatic on it. So it goes from A to B by being compressed. Now, compressed means you're doing work on the gas. And our second law of thermodynamics says that the change in internal energy is the heat added to the system minus the work done by the system. So when I say the gas is being compressed, that's work done on the system. So that's a negative amount of work. So just keep that in mind. The gas is then further compressed from B to C, where VC is equal to 0.5 cubic meters in an isothermal process. What they want to know is A, what is VB? And B, what is work total? And that means from A to B to C. So that's what we've got to solve for this problem. And I'm going to go ahead and show you how to solve it. So first off, I'm going to write solution. And with the solution, I'm going to write down some stuff we need. So we have an adiabatic process. So Q equals 0 from A to B. That implies that PA VA to the gamma is equal to PB VB to the gamma, like that. So that's one thing we know. Another thing we know is work is equal to the integral of P dV. So that's going to come in handy as well. So let's start on part A. What I'm going to say is PA times VA. So I've got 100 kilopascals times 1.00 cubic meters raised to the, remember it's 5/3, so I'm going to put 5/3 there, is actually equal to VB, or excuse me, PB, which we do know is 200 kilopascals times VB to the 5/3 power. Does everybody follow what we did there? I'm putting in the numbers. That's not normally the way I do this. I normally work at the symbols, solve it all, and then go from there. In this case, I chose to do numbers just to hopefully make it a little clearer to you guys. So what I'm going to do now is divide both sides by 200 kilopascals, and that would say 100 over 200. Notice the units have completely canceled out now. Times 1.00 meters cubed to the 5/3 power, like that. That's equal to VB to the 5/3 power. What I'm going to do is I'm going to raise this side to the 3/5 power and raise this side to the 3/5 power. Okay, not multiplying, I'm actually raising it to a power. So I end up getting 1/2. Oh, I should probably switch back to red. So I end up getting 1/2 raised to the 3/5 power times 1.00 cubic meters raised to the, remember it was 5/3, and now I raised it to the 3/5. That means you're supposed to multiply. So this is just to the 1 power, because 5/3 times 3/5 is 1. And then that's going to give me VB like that. So I could, in fact, now say that VB is equal to, I'm going to put in my calculator, 0.5, and I'm going to raise it to the parentheses 3 divided by 5 power, close parentheses. And that equals, and by the way, I am taking the 1 cubic meter and raising it to the 1 power, but that just gives me 1. So this is 0.6598. Way more sig figs than I was given. 6598 cubic meters is VB. So we've now done part A with just that. Anybody have any questions on that one? All right, so now we can do part B, and part B is going to be the work from A to B plus the work from B to C. Now, the key part to remember about this is this work is isothermal. And notice it was compression 2. You can see from B to C, the volume got smaller. So that's a compression 2. So I'm going to say that's a negative amount of work. And this one right here is adiabatic. And that was, of course, we already talked about it. That was a compression as well. So both of those are going to come out, and whatever they are, I'm going to make them negative. Okay. So let's continue on the next page with that. I am going to now say, okay, example 19-5 part B continued. Okay, so I'm going to do the work from A to B, which is adiabatic. That's equal to the integral of P dV. Oops. That is equal to the integral of P dV. Now, since it's adiabatic, what we know is PA VA to the gamma is equal to P anytime later times V anytime later gamma, as long as you're somewhere between A and B. So what that tells us is that P, if I wish to, I can take P and solve for it. And what I'll get is P is equal to PA times VA over V, all that raised to the gamma power. So that allows me to put that in here, and I'm going to say PA, which we know is a constant, times VA to the gamma power times dV over V to the gamma power. And we're going to integrate, of course, since it's over volume, I'm going to integrate from VA to VB. Does everybody follow why I did what I did? Anybody have any questions on that? So this PA and VA to the gamma, they're just constants that are going to come out in front. In fact, it's 1.00 cubic meters was PA. And VA was 100 kilopascals raised to the 5/3 power, like that. Let me make that a little clearer. Raised to the 5/3 power. Now the integral of dV times V to the negative gamma is in fact V, well, we'll put this in the bottom. It's going to be negative gamma plus 1, because that's what the integral of a power is. You add 1 to the exponent and divide by that. And now the exponent's going to have this new value of negative gamma plus 1, which we can really write as 1 over gamma minus 1. Notice if you multiply that, oops, just left off something really bad there. Left off the whole V, that would be problematic. V to the gamma minus 1. Notice if you multiply that gamma minus 1, put it in parentheses, and then multiply by negative 1, you end up getting negative gamma plus 1, which is like the denominator in that other fraction. So this is going to be taken from VA to VB. So when I take 100 cubic meters, I'm just going to get 100 cubic meters. This is going to be, or excuse me, 1 cubic meter. 1 cubic meter times, now I'm going to take 100 and raise it to the 5/3 power. And in fact, I'm also going to make it 100,000. So 1e to the 3, I'm going to raise that to the parentheses, 5 divided by 3, close parentheses. Oops. Oh, no wonder. 1e to the 3. I'm going to raise that to the parentheses, 5 divided by 3, close parentheses. And that gives me, actually, that should have been something I could have done already. Yeah, so you're basically taking the cube root of 100,000. 100,000, in fact, has 1, 2, 3, 4, 5 zeros. And then you're raising it to the 5th power. So one thing you can look at it is it's 5 zeros raised to the 5th power. That's going to make 25 zeros. And then you take the 1/3 power. So that ultimately comes out to, oh no. Okay, now I see why. It's supposed to be 100e to the 3. If it was 1,000 e to the 3, then yeah, it would have came out to an even number. That's what I kept getting, but I was evidently leaving off a number. So I said 100e to the 3 raised to the 5 divided by 3. That's not going to be an easy root. That's going to be 2.154. That's more than enough sig figs. 2.154 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. Now notice that unit actually comes out to the pascals to the 5/3 power. So that's newtons per meter squared to the 5/3 power. That could be a bit of a problem, but we're going to deal with that later. Now the gamma is 5/3, so negative 5/3 plus 5/3, or I mean plus 3/3. gives you a negative 2/3, which basically makes a negative 3/2 in front. Okay, so that's me dealing with that constant. Now all I have to do is do 1 over VB. So this will be 1 divided by, now VB was the pressure we just found, and that was or excuse me, was the volume we just found, 0.6598. So 0.6598 cubic meters. And this is to the, notice gamma minus 1 would be 5/3 minus 3/3. That's going to be 2/3. So it's going to be to the 2/3 power down here. And then from that, I'm going to do 1 over VA, which is 1.00 cubic meters, again to the 2/3 power. Now notice if you take a cubic meter and you raise it to the 1/3 power, that just becomes a meter. And then you raise it to the 2 power, that becomes a meter squared. So what we have in the bottom really is just a meter squared as far as the unit goes. And we can look at that when we start to do this math here. So I'm now going to take this and say negative 1.5, that's the negative 3/2, times 1, which you don't have to write, of course, times the 2.15 times 10 to the 8th. Then I'm going to say times parentheses. I'm going to do another set of parentheses and say 1 divided by 0.6598. And I'm going to raise that to the 2/3 power. And then I'm going to close that parenthesis because that's the first fraction. And then I'm going to go minus. Now this part's really wonderful because 1 over 1 to the 2/3 power is just going to be 1. So I'm just going to say minus 1 here and then close off that second parenthesis. And that gave me negative 1.032 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 times 10 to the 8th. And if you carry out this process, what you'll see is I've got a Newton to the 5/3 over a meter squared to the 5/3 times a meter cubed from the thing I had out in front, and then over meters squared in the bottom. That's because the meters cubed raised to the 2/3 power, the 3 cancels out and you just get meters squared. So I think you can see that this square meter is going to cancel out both of those and leave just a 1. This 5/3 is really a pain in the butt. And the units aren't working right with that very well. Oh, got a student coming in. Hold on a second. When I worked it out, I did get joules, or excuse me, I did get Newton times a meter. But right now I'm trying to figure out where I got that or how I was able to get that, because right now it's not looking so pretty. I did have P, that's in cubic meters. I had V, that's in newtons per square meter, which is what a Pascal is, but that's raised to the 5/3 power. And then the VB, yeah, that's works out that way. And that's the pressure this way. So, I guess I can break this up and do it as, oops, negative 1.032 times 10 to the 8th. This could be a kilogram meter per second squared. That's what the Newton is. And then there's a meter squared in the bottom. And both of those are to the 5/3 power. So I can write it like this, it's to the 5/3 power. And I still have a single meter here. Notice when I do that, I end up getting nothing that looks very helpful at all. Did I make any mistakes? So P is equal to PA over V to the gamma. That works okay. V to the gamma. This becomes V to the gamma plus 1 in the bottom. Ah. Hello. Oh, okay. I see what happened. Does anybody see what happened here? It's a bonehead mistake by me. Do you notice that I put cubic meters in for PA? So everything's right. I just put the wrong numbers in the wrong slots. Let me fix this real quick. This is not supposed to be that. This is supposed to be 100 kilopascals. This is not supposed to be that. This is supposed to be 100 cubic meters. That makes everything a lot more correct. I was thinking I made a mistake in the bottom, but I kept looking at that and that was working right. So this number is not supposed to be 1.00 cubic meters. This number is supposed to be 100 kilopascals. This number is not right at all. What I'm going to do is I will erase everything after that and I will put the correct numbers in. So everybody understand what I did wrong and why I shouldn't drink before coming to class? Just kidding. You know, I don't drink before class or otherwise. Okay. All right. So here this is. So this will be negative 1.5. That's what 3/2 is, times 100 e to the 3. I don't necessarily need to do e to the 3, but actually, yeah, I'll keep it as K because I'm going to use this K anyways because it's going to come out in kilojoules. So I'm going to say instead of 100 e to the 3, I'm just going to say times 100. And then I'm going to say times, now I've got 1.00 cubic meters raised to the 5/3. Well, the third root of 1 is 1. The fifth power of 1 is 1. So 1 to the 5/3 is just 1. So I get negative 1.5 times 100 kilopascals times 1.00. Now notice, yes, the 1 makes it through the 5/3 unscathed, but the cubic meter is going to make it through unscathed as well because the cubic meter raised to the 1/3 power gives you a meter, and then raised to the 5th power gives you a meter to the 5th. So that's ultimately what that is. And I still get the negative 2/3 in the bottom, which is where that negative 1.5 came from. And now I'm going to get 1 divided by 0.6598 cubic meters. All this is raised to the 2/3 power minus 1 over 1.00 cubic meters. All that raised to the 2/3 power. So this front number is basically going to be negative 1.5 times 100 times 1.00, which is obviously 150, negative 150 kilo. Now the Pascal is Newton per square meter. So when I multiply it by meters to the 5th, 2 of those are going to cancel out. I'll write right here. This is newtons per meter squared. 2 of those will cancel out and leave a 3 there. So this is going to be newtons times cubic meters. Now this other part is 0.6958. That's going to be raised to the, another way I can do it is just make it a negative, negative 2/3. So negative parentheses 2 divided by 3, close parentheses, close the other parentheses, and that is 1.2735. And notice the units here, the cubic meter becomes a meter and then raised to the second power. So this would be meters to the -2. And then this one would be -1 times meters to the -2. The meters to the -2, notice, is going to cancel out with that and just leave a single meter up top. And 1.2735 minus 1 is just 0.2735. So I'm going to multiply that 0.735 times -150. And that is going to give me, oops, that's going to give me -41.03. Actually, I shouldn't. Only this 3 is not a significant figure. So I've got kilojoules for that answer. And notice it did come out negative. So we're okay. We don't have to do anything special with that. We just know it's going to be negative. And that's just the part of the work from A to B. Now we've got to do the work from B to C. So there's one part. I'll just underline it so we can find it. Now the work from B to C, which is isothermal, is going to be equal to the integral of P dV. Now the integral of P dV is a little easier because we have PV equals nRT, and the N, the R, and the T are all constant. So we can solve for P and from the ideal gas law, and we'll get nRT over V. So that's going to be N times R times T. And it is isothermal, so it's the temperature that we have from part B to part C. So, and in fact, I think that temperature was at the 300 Kelvin. No, that was part A. So I still got to figure out what that 300. Oh, no, I don't. I remember. So there's an nRT there. And now it's the integral of dV over V because the P was replaced with nRT over V. I'm going to integrate this from VB to VC like that. Now, here's the good news. This is supposed to be nRT for the particular value of, since it's isothermal, this should be T sub B R T sub C because it's isothermal, they're the same, right? So the main thing is I just need the nRT for state B, but guess what? The nRT for state B is the same thing as PB times VB. So I can go ahead and say this is going to be pressure at B times volume at B because the left-hand side of the ideal gas law is PV, and I have the right-hand side nRT. So I can just put that there. And then the integral of dV is over V is just going to be the natural log of VC over VB. So that turned out to be a lot easier than we thought. The pressure P sub B is in fact going to be the 200 kilopascals. So I'm going to say 200 kilopascals times the volume at B. And the volume at B, of course, was the 0.6598, if I remember correctly. 0.6598, yes. 0.6598 cubic meters. That's the P times V. And now I'm going to take the natural log of VC over VB. And we know that the volume at C was 0.50 cubic meters. And the volume at B was 0.6598 cubic meters. So that's what we're taking the natural log of. So I'm going to say 200 times 0.6598 times natural log parentheses 0.5 divided by 0.6598 close parentheses. That gives me negative 36.60. Notice the pascals, Newton per square meters. I'm multiplying that by meters cubed, so that becomes a Newton meter, which is a joule, and the kilo stays the same, so it's going to be kilojoules. So that's the answer there. Notice it did come out negative, so we're golden with that. So the net work done in going from A to C, which was what we were asked, the work from A to B to C total was in fact negative 41.0 kilojoules minus 36.6 kilojoules, which gives me about 77.6 kilojoules negative. And that's basically it. I don't know why I got 41. I got 48 last time, so there might be a mistake in this. I'm going to say I got 47.8 or something like that. And that actually would give 48 kilojoules minus 37 kilojoules equals 85 kilojoules. Again, negative. This is correct. I know that for a fact. So I made some kind of careless arithmetic mistake in the one above. 150 times 0.2735. That's still 41. Yeah, I'm not sure where I made a mistake, but there's definitely an error in there. So just keep an eye out for that. I'm actually looking at the other one. They had 3 halves times 100 times 1. That all looks good. They rounded it to a plain 0.66. That could actually make the difference. Let's see, 0.66 to the negative 2/3 power. 1.31. So I'm going to subtract 1 from that. And now I'm going to multiply that by 150. That's it. So yeah. All I had to do was if I used 0.66 cubic meters, then V, oops, not there. If I use 0.66, whoa, no, I did not mean to do that. If I use 6.6, then work from A to B would equal negative 47.88 actually kilojoules. So that's been corrected now. I've got the correct answer. Any questions on that? Sorry about that. Thinking that was going to be a really big deal as far as the screw up, but it turned out to be something really small, so that was helpful. So yeah, if I just would have rounded that to 0.66 instead of using 0.6598, that would have gave me a better figure, but it's close enough. If this was a multiple choice and you got negative 85 and I had negative 78, that's the closest one. That's scary, but it is what you're supposed to do, so you would get it right. And I would be responsible for that. So if I had a multiple choice and I had a 88 and a negative 78, then I would have to mark both of those correct. once I looked at your work or once I did my own work or that sort of thing. So any questions on that? All right, so that's sort of the last real ideal gas law type problem that we're doing for chapter 19. And in fact, the rest of it is all about being able to talk about how you can transfer heat from one object to another. So in fact, it's very straightforward calculations, at least for conduction and radiation. And I'm going to give you those formulas. The first one I'm going to motivate. And your book doesn't even feel compelled to show any examples. They're that straightforward. Or actually, I think it might show an example with conduction, but not with convection. Well, definitely not with convection, because that's really a nasty, complicated thing. I'm trying to look. Yeah, they do show one example with the conduction. So that's pretty straightforward. You can look it over. It's example 1916, but they don't show any examples with radiation. So what I'm going to tell you is that the second law of thermodynamics, at least one version of it. So what you're going to learn in chapter 20 is about the second law of thermodynamics. That's the whole reason I'm covering chapter 20 at all. I don't care too much about all the details of it. I mean, I like them, and I think you should be steeped in that kind of stuff if you're going to be a physicist. But if you're going to be an engineer, then there's parts of that you should be steeped in, but you'll get that from your engineering thermo class. They often call it steam table thermodynamics and stuff like that. But the main thing is you'll get plenty of education from that. And if you're going to become a physicist, you'll get plenty of education when you take your actual thermodynamics class. So I don't feel too bad about skipping this. But basically, there's a bunch of ways you can say the second law of thermodynamics. One of them is the second law of thermodynamics says that heat will flow spontaneously from a hot body to a cold body. What I mean by spontaneously means if you take a hot object and put it near a colder object, and that means a hot object means one whose temperature is higher than one who's considered a cold object. If you put them next to each other, we know on the microscopic level that the hot object, the individual atoms or molecules, have higher kinetic energy than the cold objects. Therefore, it's sort of like you have a bumper car set up at, like, King's Dominion or Busch Gardens or something, only some of the cars are all full-size cars and the other cars are just regular bumper cars. So you can imagine the bigger full-size cars are going to hit these small bumper cars and give them a buttload of speed. And what's then going to happen is that isn't a change in temperature. What's a change in temperature is when the average kinetic energy goes up. That's the change in temperature. So what's going to happen is, 3, 4, 5 of the smaller bumper cars run into the big cars. They come off flying really, really fast. And then they're going to collide into some of the other smaller cars. They make them speed up a little bit. And then some more come in and hit the big cars. They speed up. They hit some more cars. And keep doing that until basically almost all of them have hit the bigger cars. And then the net average kinetic energy of the smaller cars has finally reached the same net average kinetic energy as the bigger cars. That's the very definition of temperature. Therefore, the two bodies are at the same temperature. So heat flowed from the hot object to the cold object until the temperatures became the same. That heat flowing on its own from the hot object to a cold object is a statement of the second law of thermodynamics, but it's not the only one. And all of them have been shown to be equivalent. So your main thing about chapter 20 is I want you to be able to state all the versions of the second law of thermodynamics, and they're just listed in your book. I need you to be able to calculate the efficiency of a Carnot engine. So there's a very specific formula for that. It's 1 minus T cold over T hot. And it's also 1 minus Q cold over Q hot. That's the fundamental definition of the efficiency of the Carnot engine. But we can actually do a derivation and show that that's equivalent to 1 minus T cold over T hot. And since you can do that, then you can use it. So those two ways you need to be able to calculate the efficiency of a Carnot engine, and you need to be able to state the individual versions of the second law of thermodynamics. And another version of it is no heat engine can be more efficient than a reversible heat engine. And the efficiency of a reversible heat engine is the maximum efficiency possible. So that's another version of the second law of thermodynamics. Another version is the a quantity called the, oh darn, I just lost the quantity. Entropy, that's it. So there exists a quantity called the entropy that can be expressed as a differential ds, because s is a state variable. So ds is equal to d bar q. Remember, we talked about d bar as opposed to just d. So ds is equal to d bar q over t. That's called the entropy. And in a reversible process, the entropy remains unchanged. And in all real processes, the net entropy of the universe increases. So in all real processes, the net entropy of the universe increases. In all real processes, the net entropy of the universe increases. In reversible processes, it stays the same. So that's another version. Clean it up, use the words, but it's basically going to be like a multiple choice sort of scenario where I'll have a bunch of laws listed and you state them. That means you're still responsible for the first semester. So you still need to know Newton's first law, Newton's second law, Newton's third law, Kepler's first law, Kepler's second law, Kepler's third law, and maybe conservation of momentum, conservation of angular momentum when they're true, for instance. And then you need to know, of course, the first law of thermodynamics, the second law of thermodynamics in all its forms, the zeroth law of thermodynamics, which your book talked about, and I quickly hinted at, and you might even find a third law of thermodynamics, but I'm not going to ask you that one. So that's the main thing you got to know about that. So now that we have that out of the way, we sort of covered chapter 20 to some extent, and we're going to do more. But now I got to finish up with what I was talking about heat flowing from a hot body to a cold body. The three ways that heat can flow from one object to another, and this is the only three ways. There's conduction. And notice that duck sounds a little bit like touch. So that's what I used as a mnemonic when I was younger. I would say conduction is when two things are touching. And I try to make that syllable long so that I could hear it. But basically, when two objects are touching, they are conducting heat from the warmer one to the colder one through conduction. I have an equation for that. We're going to show it to you in a second. Another way is convection. So you might imagine, for instance, let's say we're going to heat up the air in a room, and we're going to do it using a burner and water. Okay, this seems kind of weird, but this is making a point. So if you take and stick a pot of water on a stove, electric stove, what will happen is the electric stove, when you turn it on, that's going to start heating up the bottom of the pot. That pot is going to cause the water right adjacent to the bottom of the pot to get hotter. When it gets hotter, like all things, they expand at higher temperature. That means the density is going to decrease. So the density decrease is going to cause that slightly warmer fluid to float to the top. It's going to get to the top, and then it still will be a little bit warmer than the rest of the surroundings. So that heat can be delivered directly to the air. That cyclic process through that third medium is really what the convection is about. So this is the type of stove, for instance, that 7-Eleven has now, where they can cook burritos and pizzas in a couple of minutes. It's also the same thing that you guys might have at home. Your wife might have, or your boyfriend or whatever, might have had some interest in an air fryer. That's basically what an air fryer does, is it allows not only heat, so there's like little wires in there, like or tungsten type wires, like what you'd see in a toaster oven. And those are going to provide heat through radiation, convection, and conduction. You're going to then have a blower that blows that heat across the food from all different angles. So that air going across is going to deliver that heat to the food you're cooking. That's what makes it convection. And that's what makes it a little faster, because you're still getting the radiation. You're not getting as much conduction directly, because there's only parts of the meat or the food that you're cooking that are actually touching, but you are getting convection as well from and it's sort of convection. You're not fighting gravity here. You're using wind blown by a fan, basically. So it's not, in that sense, convection that uses gravity, but still you're delivering more heat than you otherwise would. That's why you can cook things a little quicker. So that's the second mechanism, is convection. As you can tell, that requires fluid mechanics, and flow would be constant complicated because it's not necessarily laminar flow and all that stuff. So we don't really have any good equations for that, but it's a ripe area for research if you're interested. The third way is radiation. So let me give you the equation for conduction first. So we're looking at right now a blank screen. And what I'm going to tell you is what is relevant is the amount of heat added. I'm not going to use a delta. I'm just going to use a Q. The amount of heat added divided by the time taken. That's really what's going to matter. So this is conduction. And I'm going to have you imagine a scenario, and we're going to use just good common sense to figure out the right answers. So for my diagram, I'm going to imagine what we call a heat sink or a heat reservoir. And what I mean by that is sort of like a lake. You know, a lake is really, really big. So a lake can actually take a ton of heat before it actually changes temperature. So in that sense, if you're talking about compared to a human jumping in the water, then a lake is a heat sink, because no matter how many humans you jump in that lake, it's not going to change its temperature. So I'm going to have over here a heat sink whose temperature is T hot, or T sub H. And then I'm going to have a rod that has a circular cross section. The area of that rod cross section is A. And that's going to come over here like this. And again, you're going to have an A cross section there as well. But over here, I'm going to have another heat reservoir. And this heat reservoir is actually going to have a temperature of T cold. Like this. And in fact, I'm going to say this distance right here is L. And that area is A. So first off, if you're talking about how much heat is going from TH to TC, and that's by the second law. Okay, if you're talking about how much heat is going to go from TH to TC per unit time, do you think A being bigger would make more heat go per time, or would A being smaller go cause more heat per second? So the big question is calories per second, cross-sectional area, thumbs up, or thumbs up, thumbs down. If you've ever had like a cold hand from being out in the snow, you might decide to take your hand and, you know, lay it on your significant other's back, for instance. And if you just lay like this little part, that part feels pretty good. But then you realize, well, wait a second, my whole hand's freezing. So you try to put the whole hand, never mind what's going to happen to the significant other. They're not going to be very happy about this, but you go on with your experiment. That's how that thing works. So when you do that, what you discover is the more hand that you get in contact with their warmer body, the more heat's delivered to your hand, and the quicker your hand feels better. So that would suggest that Q over delta T is thumbs up with A. And that's exactly right. Now, do you think Q over delta T is thumbs up with L, or thumbs up, thumbs down with L? Anyone? Well, you can imagine if you actually connected your hand through something the shape of your hand, and it was maybe a millimeter thick, and you put it between your hand and your significant other's back, that would be a little bit inconvenient, not quite as happy, but they would feel a little better. They're not losing as much heat. But if you did it with something that was, say, a mile thick, then you'd see that it's not very effective at all. So that tells you that Q over T is thumbs up, down with L. So I'm going to put the L in the bottom. You'd also figure out that the bigger the temperature difference is. So if my hand's like 50 degrees Fahrenheit and my wife's back say is 98.6, that's a big temperature difference. But if it was just a 97 and a 98, there wouldn't be much heat flow. So we think the delta Q over delta T is thumbs up with delta T. And this is a different delta T. This is a delta T meaning temperature. Now, all that it takes to make this a equation is a constant of proportionality. And then we decide, wait a second, we need to take into account the property of the material, which is what this tube is made of. And that tube has a thermal conductivity of K. So ultimately, the equation becomes delta Q over delta T. That's time, by the way, which is essentially dQ over dt is equal to Ka over L times delta T. So that's one equation. Like I said, you can see example 1916 on how to do that. The one for radiation is a little different. I'm going to write that down now. And you guys, of course, are free to go. We've ran out of time. I will wait for the last person to leave before I leave, but I'm going to go ahead and finish out this thought. What we find is that the heat put out per time, which is also called the luminosity. And the luminosity, by the way, which is the same thing as Q per delta T, has units of basically joules per second or calories per second or watts. Okay, well, that turns out to be the emissivity times the Stefan Boltzmann constant times the surface area times T to the fourth. So this is the surface area of the thing of temperature T. Okay. The bigger the surface area, the more heat that's being put out. That's sort of like you putting a really big pot of water to boil on a small burner. Doesn't work too well. Whereas if you take that same pot and put it on a burner the same size as the bottom of the pot, it works better. This is 5.67 times 10 to the negative 8 watts per square meter Kelvin to the fourth. That's the Stefan Boltzmann constant. And this is called the emissivity, which I can't remember if it's 2 M's or 1. I think it's 1 M ISSI TIVITY. Okay. That would be one for what we call a black body, which is a perfect emitter and a perfect absorber, and it's something less for everything else. It also has to do with the albedo, for instance, of a planet. But that's it. And they don't even give you an example for this one. So this is the other equation you've got to be able to use in the simplest cases. So that's it. We're done with chapter 19. And we've done a little bit of chapter 20. Anybody have any questions? No questions? Sang, Gavin.
I'm
All
good,
right.
thank you.
Sorry for taking so long, guys. Y'all have a good one.
Bye.
See you, Thing. I'm going to say see back. See next page. So you guys have already looked on, of course, but I wanted to reiterate what I just said regarding chapter 20. Oops, let's not do that. Let's do regarding chapter 20. 1. Know all versions of second law of thermodynamics from chapter 20. the way I'm actually planning on delivering that type of question would be a multiple choice where you have a bunch of things to click on. And I might ask you stuff from last semester as well. So I'm going to say no Newton's first law, second law, third law. Now, I mean, know the law and know which one's the first, which one's the second, which one's the third, and universal law of gravitation. Kepler's first law, second law, and third law. No law of conservation of linear momentum. The main thing is know what is actually required for momentum to be conserved. I've covered that 1,000 times when we discussed momentum. You can just look in your book on the chapter on linear momentum, P equals mv, and find under what conditions P is conserved or P is a constant. I will give you the big hint that Newton's second law of motion can be written as the net force is equal to dP, the momentum, over dt. So the instantaneous rate of change of momentum with respect to time. Know the law of conservation of angular momentum. That's the L. Again, the same thing here. I will let you know that the summation of the torques is equal to dL dt, where L is the angular momentum. And that gives you a big hint on what's required to be true for angular momentum to be conserved. So you need to know that. You also need to know the 0th law of thermodynamics. This the first law of thermodynamics, which I told you guys is basically conservation of energy. And you need to know the second law of Thermo. Always given in chapter 20. So in other words, there's a bunch of versions of the second law of thermodynamics in chapter 20. They're all equivalent, even though they don't seem to be, with perpetual motion things and stuff like that. But you should know all of them for that test. And then 3, of course, in addition to all that, you should be able to calculate efficiency of a Carnot engine. And really, to be honest with you, everybody should know how a Carnot engine works, which is really the holy grail I'm going for. I'm just not going to ask you those questions except in your homework scenarios. So I'm just telling you, for the test, you need to know how to use the formula for the efficiency of a Carnot engine. One of those formulas is efficiency E is equal to 1 minus, actually, let's do the original one. So this is Q cold over Q hot, but it also equals 1 minus T cold over T hot. Okay, but in general, the efficiency is work divided by total heat added. Okay, so you do need to know how to calculate the Carnot efficiency using either the temperature or the heat added, that sort of thing. Know how just to do simple Carnot engine problems. And 5, just going back to not necessarily the Carnot engine, but in general, what was I getting ready to say? There's a simple Carnot engine problems. Work is equal to this, work is equal to that. That works fine. There was something else I was going to say. Calculate efficiency of Carnot engine. Simple Carnot engine problem. DS. Actually, let me write that a little neater. So the differential change in entropy is d bar q over t, and S equals K ln W. So you'll look in chapter 20, and you really need to know this version and specifically what it's saying, because this is where you hear what seems to be absurd comments about the second law of thermodynamics. Like the second law of thermodynamics is the reason it's easier to pull out of a parking space than it is to pull into a parking space. And it sounds like BS, but it is actually correct. And this S equals K ln W, where W is the number of microstates. I want you to know that. So just make sure you know that, and know that this is the definition of entropy. DS is equal to d bar q over t. So that's the main stuff you need to know. I'm going to show you some examples next time, and then we're going to jump right into chapter 21. You guys have a good one. I hope that helped you prepare. So do check it out, and I'll see you later.